Okay, so we have been talking about chapter 4, torsion and torsional elements. Okay, last time we already started to introduce the stress in torsional element, and we derived the equation to calculate the shear stress in the torsional element. Okay, here is a video. Please click here. You will have a video to show a lot of real-world examples of a torsional element and the basic introduction of torsion and torsional stress and strain. So last time we already derived the equation to calculate the shear stress in a torsional element, and we started from this two, and we derived that the tor max, the maximum shear stress in the torsional element equals Tc over J. So here the C is the distance from the center to the edge, right? So that is the maximum shear stress in the torsional element. And at the random point here, with the distance from the center rho, those shear stress equals tau rho over J. So you can see that these two, the shear stress in the torsional element is actually directly proportional to the distance from the center. So you can see from here the distribution of the shear stress along a diameter direction will be something like this. Okay, you have the maximum value here, tau max, and here tau max, and other smaller shear stress values in a random point between the center and the edge. So at the end of the direction here, last time we already showed that the surface integral leads to this value, so pi over 32 by d to the fourth. So we denote this thing with J, with the big J, and we call it polar moment of inertia. So in this way, we'll have the equations. And today we will talk about how to use these equations to analyze the stress in a torsional element. Today we will have two objectives. The first one, we will analyze torque and stress in a torsional element. So here the torque is internal torque. So the same as previously when we talk about the actually loaded element, there you need to determine the internal force. But here we're also determining internal force, but here is the kind of torque. It's not axially loading, not axial loading or normal stress. And then we will start to talk about deformation of the torsional element. Okay, here are the two equations to calculate tau max and a random tau at a random point. So you can see directly that the tau over tau max equals rho over C. Okay, meaning that the shear stress at a point is directly proportional to the distance from the center of the torsional element. So you can easily see that at the center here, the tau equals 0, and at the edge, tau equals tau max. Again, I need to emphasize that the T here in this equation is internal torque in the shaft. And the C or rho C is the maximum distance from the center, and the rho is the distance of the point at which the stress is being calculated from the centroid of the section. So J is the polar moment of inertia. So we will only deal with these two cases. You will not be given any square-shaped or rectangular-shaped torsional elements. We will only deal with circles. Okay, for the solid circle shaft, the J equals pi over 32 d to the fourth. And for a tubular shaft, so you will get pi over 32 d. This is the external diameter to the fourth minus the internal diameter to the fourth. Okay, to analyze the stress in a torsional element, we will follow similar steps as the axially loaded element. So the first step is to determine the internal torque, the internal force, but in this case is the internal torque, T. Right? Of course, you need to use free body diagram. That is always the first step of stress analysis. But later we will show how to do free body diagram and how to determine the internal torque in a torsional element. Then step 2 will determine the polar moment of inertia. As I just mentioned, we will have only these two cases. Okay, you will not be given any more complicated shapes. Then we will just determine the shear stress caused by torque by using this equation. Tau, the shear stress, equals torque by C over J. Okay, here the C is the distance from the point to the center. Okay, in the first step of stress analysis, as we mentioned, we need to use free body diagram to determine the internal torque. Here are the 3 steps to determine the internal torque in the torsional element. The first step of free body is always to cut the element to make it free. You have to find the point of concern first and then cut it, make it free, then apply forces and make it outward from the cut surface. Okay, the same as the actually loaded element. Here, as you can see in this example, if you want to determine the internal torque in the section AB, right, you just need to cut it from a random point between A and B and make it free as shown here. Then you add the internal torque T1. We use a double-headed arrow to denote T1 to denote the torque. Okay, but later you will see that you will have TB, TC, and TD. Right, it's 3 external torques. But how to denote them here? We need to build a equilibrium equation. Okay, the sum of all torques equals 0. Here you have a left pointing T1, but you have TB, TC, and TD in this kind of direction. So here we need to use the right-hand rule to convert them, to convert TB, TC, TD into double-headed arrows. Here I think everyone knows how to use the right-hand rule. So you will just make sure curl your 4 fingers of the right hand according to the direction, following the direction of the torque. And then the direction of your thumb will be the same as the double-headed arrow. So look at B, look at TB. So if you make your 4 fingers of right hand, curl those 4 fingers in the direction of the TB, you will see that your thumb will be pointing right. Right? So here you will get TB in this way. So this is the equivalent TB. So here you look at TC, it will in the same direction. Right? You have TC. And here TD, the same direction. So based on the first free body diagram, so you can get a equilibrium equation. So that is negative T1 plus TB plus TC plus TD equals 0. Okay, in the same way, in the second one, if you want to determine the internal torque between B and C, right, just cut it from here, make it free, and add a T2 here. And then you will denote the TC and the TD using double-headed arrows. You get negative T2 plus TC plus TD equals 0. With the last one here, you just add TD, you get negative T3 plus TD equals 0. So here you can solve everything. You can solve TD first of all, right, then TC, then TB. So you can solve all of these internal torques in section AB, section BC, and section CD. Right? So you can solve these torques, and then you know the C or rho, and then you can calculate the J, so you can analyze, you can calculate the stress, shear stress at any point through the cross section of a torsional element.